Welcome back to my channel Shri Statistics. Today we are going to start the Markoff's theorem, and for this particular video, particular theorem, there will be a series of videos covering the entire proof in different parts. So today we start with the first part of Markoff's theorem. This theorem is for the case when the observations are independent and the coefficient matrix is of full rank. So the statement is that let y is equal to x beta plus e. So y over here is a vector of n observable quantities. X is the matrix of known coefficients of order n cross p. Beta is the vector of unknown quantities known as effects, which is a column vector of order p. E is the error vector, and let this entire thing be a general linear model. Here there are two assumptions, that expectation of E is equal to 0 and variance of E is equal to sigma square I. That is, these error terms are all independent. So if the rank of X is P, that is, if X transpose X is a matrix of full rank, then the best linear unbiased estimator of beta is given by the method of least squares. The unbiased estimate of sigma square is given by this quantity, where SE is the sum of the squares of the residuals. So to prove the first part, for the method of least squares, we minimize the error, that is the residual sum of squares. So in the general linear model, y is equal to x beta plus e. The error sum of squares is equal to this quantity. So on differentiating this quantity with respect to beta and putting it equal to 0, we follow the usual method of differentiation, and then you can see that we expand this, and hence we differentiate each term separately. So here there is no beta, so over here we have 1 beta, so this is obtained. Similarly for this, and here we have beta prime x prime beta prime x beta, so here we get 2x prime x beta. So this is minus 2x prime y minus x prime y. Here this will become minus 2. On putting these equal to 0 and solving, we get x transpose x beta is equal to x transpose y. This is equation number 1, and this equation is known as the set of normal equations. So since the rank is equal to P, as we have assumed over here, then x transpose x is a non-singular matrix. Hence from 1, that is this equation, we have beta cap is equal to x transpose x inverse x transpose y. This is equation 2. Beta cap is the least square estimate of beta. Now, if S is equal to x transpose x, then beta cap is equal to S inverse x transpose y. So this is from equation 3. Now, if the matrix formed by this is denoted by A, which is of the order P cross N, then if A is denoted in this way and beta cap is equal to AY, therefore each value of beta cap, that is beta I cap, will be equal to AY1 and Y1 plus AY2 I2 and so on solving this. So here we get that beta cap can be equal to j varies from 1 to n, aij, yj. I varies from 1 to p. Hence, beta cap I varies from 1 to p are linear combinations of the vector y. Consequently, the vector beta cap is linear in terms of observation vector y. So this is the first part of the proof. For the next part, it will be available in my next video. So thank you for watching.